Exploring the Arctic and Antarctic has never been a matter of bravery alone. Survival and progress in the coldest regions on Earth have always depended on machines capable of operating where temperatures can kill, terrain can swallow vehicles whole, and resupply is often impossible. Throughout the 20th century, engineers from competing nations pushed the limits of scale, power, and endurance to build vehicles that could cross ice sheets, frozen tundra, and polar plateaus while carrying people, fuel, and entire mobile bases. Some of these machines succeeded, others failed spectacularly, but all of them represent extreme responses to extreme environments. The vehicles documented here were not merely transport solutions. They were engineering statements, built to challenge geography itself and redefine what was physically possible in the polar regions. Antarctic Snow Cruiser, America's failed attempt at a rolling polar city. The Antarctic Snow Cruiser stands as one of the most ambitious and ultimately flawed polar expedition vehicles ever constructed. Conceived in the late 1930s, it was designed to function not merely as transport, but as a self-contained mobile research station capable of supporting long-term scientific exploration deep within Antarctica's interior. The project was developed for the United States Antarctic Service Expedition, which operated from 1939 to 1941 under the direction of famed explorer Rear Admiral Richard E. Byrd. The snow cruiser itself was designed by Thomas C. Poulter, a physicist and veteran polar researcher who envisioned a single vehicle that could replace sled convoys, aircraft resupply, and fixed bases. Construction took place in 1939 to 1940 at the Pullman Standard Company in Chicago. The finished machine was colossal by any standard, approximately 17 meters long, 6 meters wide, and weighing about 34 metric tons. It rode on 4 enormous smooth rubber tires, each nearly 3 meters tall, which were intended to float over snow rather than dig into it. Inside, the snow cruiser housed sleeping quarters for 5 men, a galley, laboratory space, fuel storage, and even a small aircraft mounted on the roof for aerial reconnaissance. In theory, it was a rolling polar city. In reality, it was a mechanical miscalculation. Upon arrival in Antarctica in January 1940, the snow cruiser immediately revealed critical design flaws. The smooth tires provided almost no traction on packed snow and ice. Attempts to improve grip, such as fitting chains and reversing tire tread orientation, failed to solve the problem. The vehicle struggled even on gentle slopes and was incapable of sustained overland travel. As World War II escalated, the expedition was curtailed, and the snow cruiser was abandoned near Little America 3 in 1941. It was partially buried by snow but remained structurally intact. Subsequent expeditions cited it in 1946 to 1947, still standing on its massive wheels, before it was eventually lost beneath the Antarctic ice shelf, likely carried into the sea when the shelf calved. Despite its failure, the Antarctic Snow Cruiser occupies a unique place in exploration history. It was the largest wheeled vehicle ever purpose-built for polar exploration, and its bold design influenced later thinking about mobile research platforms. More importantly, it serves as a cautionary example of how engineering optimism, when divorced from environmental reality, can undermine even the most visionary projects. The snow cruiser did not conquer Antarctica, but it permanently reshaped how nations approached the challenge of surviving, moving, and conducting science at the coldest edge of the world. Kharkovchanka Antarctic Artillery Tractor, the largest tracked polar vehicle of its era. The Kharkovchanka Antarctic Artillery Tractor was a defining achievement in Soviet polar engineering and marked a turning point in how large-scale expeditions were conducted in Antarctica. Created to solve the immense logistical challenges of inland travel, it replaced slow dog teams and risky aircraft drops with a single, self-sufficient ground vehicle capable of crossing vast, frozen distances. Development began at the Kharkov Locomotive Factory in the Ukrainian Soviet Socialist Republic during 1957 to 1958. The design was based on the ATT heavy artillery tractor, a military machine already proven in harsh environments. Engineers enlarged and reinforced the platform, adding insulation, heating systems, and structural modifications, so the vehicle could operate continuously in temperatures below -50 degrees Celsius without external support. The Kharkovchanka entered Antarctic service in 1959 with the Soviet Antarctic expedition. It was primarily deployed from Mirny Station and later became essential to operations supporting Vostok Station. At approximately 8.5 meters long, over 3.5 meters wide, and weighing more than 35 metric tons, it was the largest tracked polar vehicle of its time. Its wide tracks distributed weight evenly across snow and ice, allowing it to traverse deep drifts, sastrugi, and uneven glacial terrain that immobilized smaller machines. Unlike conventional tractors, the Kharkovchanka functioned as a mobile base. Its interior contained sleeping bunks, a kitchen area, storage compartments, radio equipment, and workspaces for mechanics and scientists. Crews could live inside the vehicle for weeks, reducing exposure to extreme weather and enabling long overland journeys without resupply. This design dramatically increased the range and safety of Antarctic expeditions. One of the Kharkovchanka's most notable achievements occurred during 1959 to 1960, when a convoy completed an overland traverse from Mirny Station to Vostok Station, a distance of more than 1,400 kilometers across the Antarctic plateau. The journey proved that heavy-tracked vehicles could reliably support scientific research deep inland, even in the coldest and most isolated regions on Earth. The vehicle remained in service throughout the 1960s and into the 1970s, becoming a familiar sight in Soviet Antarctic operations. Its success directly influenced the development of the Kharkovchanka II, which featured improved reliability and crew comfort, but followed the same core concept. In polar exploration history, the Kharkovchanka stands as a symbol of brute force engineering adapted to environmental extremes. It demonstrated that size, durability, and self-sufficiency could redefine what was possible in the tracked Arctic and Antarctic expedition vehicles. Kharkovchanka II Polar Transport Vehicle. Soviet polar engineering refined at scale. The Kharkovchanka II Polar Transport Vehicle represented the maturation of Soviet heavy polar vehicle design, building directly upon the hard-earned lessons of its predecessor. While the original Kharkovchanka proved that massive tracked vehicles could operate deep within Antarctica, the Kharkovchanka II refined the concept by improving reliability, crew comfort, and long-term operational efficiency without sacrificing scale or capability. Development of the Kharkovchanka II took place during the late 1960s to early 1970s at the Kharkov Locomotive Factory. By this time, the Soviet Antarctic expedition had accumulated more than a decade of experience using heavy-tracked vehicles in extreme polar conditions. Engineers focused on addressing mechanical failures, improving cold weather performance, and making life aboard the vehicle more sustainable for crews operating thousands of kilometers from the coast. The Kharkovchanka II entered Antarctic service in the early 1970s, continuing support for Mirny Station and Vostok Station. In terms of size, it remained one of the largest tracked polar vehicles ever fielded, measuring roughly 9 meters in length and weighing more than 35 metric tons when fully equipped. Its broad tracks and reinforced suspension allowed it to move heavy cargo and tow additional sleds or fuel trains across deep snow and hardened ice with improved stability compared to the earlier model. One of the most significant advances of the Kharkovchanka II was its redesigned interior. Crew living spaces were better insulated and more efficiently heated, reducing fuel consumption and improving survivability during prolonged missions. The vehicle featured improved sleeping arrangements, a more functional galley, upgraded radio and navigation equipment, and expanded storage for food, spare parts, and scientific instruments. These changes allowed crews to remain in the field for extended periods with greater safety and reduced fatigue. Mechanically, the Kharkovchanka II benefited from enhanced engines, transmission components, and maintenance access points, all designed to simplify repairs in sub-zero conditions. Reliability was a critical priority, as mechanical failure in Antarctica could quickly become fatal. The refined design significantly reduced breakdown rates during long overland traverses. Throughout the 1970s and 1980s, the Kharkovchanka II played a central role in supporting inland scientific research, fuel transport, and station resupply missions. Its performance confirmed the value of large, self-contained tracked vehicles in polar exploration and logistics. In historical perspective, the Kharkovchanka II stands as a clear example of iterative engineering at scale. It did not reinvent polar transport, but it perfected a proven concept, reinforcing the Soviet Union's reputation for building some of the largest and most durable expedition vehicles ever to operate in the world's coldest environments. Sverdlovsk Arctic Overland Train, a multi-unit giant built to cross the Arctic interior. The Sverdlovsk Arctic Overland Train was one of the most ambitious land transport concepts ever attempted in the Arctic, designed to solve the problem of moving massive quantities of cargo across regions where roads, railways, and waterways simply did not exist. Rather than relying on a single vehicle, Soviet engineers pursued the idea of a multi-unit land train capable of operating as a mobile supply convoy across the frozen interior of the Arctic. Development of the Sverdlovsk Arctic Overland Train took place during the late 1950s to early 1960s at industrial and research facilities associated with the Sverdlovsk region, now known as Yekaterinburg. The project was driven by the Soviet Union's expanding industrial and military interests in the far north, where oil, gas, minerals, and strategic infrastructure required reliable year-round transport. Engineers sought to replace seasonal ice roads and costly airlift operations with a ground-based system that could function continuously in extreme cold. The land train consisted of a powerful lead tractor unit connected to multiple articulated cargo modules, each mounted on tracks or large low-pressure running gear. When fully assembled, the train could extend over tens of meters in length, making it one of the longest ground vehicles ever designed for Arctic conditions. Its modular design allowed sections to be added or removed depending on mission requirements, enabling the transport of fuel, construction materials, scientific equipment, and even prefabricated structures. Operational trials were conducted during the early 1960s across Arctic test routes characterized by deep snow, uneven ice, and frozen tundra. The train's distributed weight reduced ground pressure, allowing it to cross terrain that would immobilize conventional wheeled trucks. Heating systems, insulated compartments, and cold weather lubricants were incorporated to ensure mechanical function at temperatures well below -40 degrees Celsius. Despite its impressive scale, the Sverdlovsk Arctic Overland Train faced significant challenges. Maneuverability was limited, especially in tight terrain or areas with pressure ridges and uneven ice. Mechanical complexity increased with each additional unit, complicating maintenance and repairs in remote regions. Fuel consumption was also substantial, reducing overall efficiency compared to smaller, more flexible vehicles. Although the project did not see widespread deployment, it provided valuable data that influenced later Soviet Arctic vehicle development, including articulated tracked transporters and logistics convoys. The concept demonstrated that overland transport on a near railroad scale was technically feasible in the Arctic, even if not always practical. Historically, the Sverdlovsk Arctic Overland Train stands as a bold experiment in scale and ambition. It reflected a period when engineers believed that sheer size and modular power could conquer the Arctic interior, leaving a lasting legacy in the evolution of polar expedition and logistics vehicles. Sever II Arctic Overland Train, the Soviet Union's ultimate snow convoy experiment. The Sever II Arctic Overland Train was one of the most extreme and visionary transport experiments undertaken by the Soviet Union in its effort to master Arctic logistics. Conceived as a solution to the vast distances and lack of infrastructure in the far north, Sever 2 was designed to function as a moving supply corridor capable of replacing railways and roads in permanently frozen regions. Development of the Sever 2 project took place during the early 1960s to late 1960s under Soviet research institutes specializing in Arctic engineering and military logistics. The name Sever, meaning north, reflected its intended operating environment across Siberia's Arctic interior, where temperatures routinely fell below -50 degrees Celsius, and terrain shifted between deep snow, ice fields, and frozen tundra. Unlike single-vehicle solutions, Sever 2 was designed as a true land train. A powerful lead tractor unit pulled multiple articulated cargo modules, each mounted on tracks to minimize ground pressure. When fully assembled, the convoy stretched across dozens of meters, making it one of the longest overland vehicles ever built for Arctic conditions. The modular units were designed to carry fuel, food, construction materials, machinery, and living quarters, allowing crews to operate independently for extended periods. Field trials were conducted throughout the mid-1960s in remote Arctic test zones. The distributed weight of the train allowed it to traverse terrain that conventional trucks could not cross, including soft snow cover and uneven ice. Heating systems, insulated cargo compartments, and cold-resistant mechanical components were integrated to ensure functionality during prolonged exposure to extreme cold. Despite its scale and engineering sophistication, Sever 2 faced significant operational challenges. Maneuverability was limited, particularly in areas with ice pressure ridges, sharp elevation changes, or restricted space. Mechanical complexity increased the risk of breakdowns, and repairing multiple interconnected units in isolated regions proved difficult. Fuel consumption was exceptionally high, reducing overall efficiency and operational range. By the late 1960s to early 1970s, Soviet planners began shifting toward smaller articulated vehicles, seasonal ice roads, and expanded airlift capabilities. As a result, Sever 2 never entered mass production or regular service. However, the data gathered from its trials proved invaluable for later Arctic vehicle development, particularly in the design of articulated tracked transporters and modular logistics systems. In historical context, the Sever 2 Arctic overland train stands as the most ambitious Soviet attempt to create a mobile snow convoy on a near-industrial scale. It demonstrated both the possibilities and limitations of extreme-size solutions in polar environments, leaving behind a legacy of innovation that shaped future Arctic expedition and transport vehicles. DT-30PM Vityaz Arctic Transporter, the heaviest operational articulated snow vehicle. The DT-30PM Vityaz Arctic Transporter is widely regarded as the heaviest and most capable articulated snow vehicle ever placed into regular operational service. Designed to function where conventional vehicles fail completely, it represents the peak of Soviet and later Russian expertise in extreme cold mobility, combining massive payload capacity with exceptional terrain adaptability. Development of the Vityaz family began in the late 1960s, but the DT-30PM variant emerged as the definitive heavy-lift model during the 1980s to 1990s. It was developed by the Vityaz Machine Building Company to meet military, industrial, and scientific needs in Siberia, the Arctic coast, and polar regions where temperatures routinely fall below -50 degrees Celsius. Unlike experimental land trains, the DT-30PM was designed for continuous, real-world operation. The DT-30PM consists of two fully tracked units connected by a heavy articulated joint that allows vertical and horizontal movement. This articulation enables the vehicle to climb steep obstacles, cross pressure ridges, and traverse uneven ice fields without losing traction. Fully loaded, the vehicle weighs over 60 metric tons and can carry payloads of up to 30 metric tons, making it the largest articulated tracked transporter to see sustained service in Arctic conditions. In terms of dimensions, the DT-30PM measures roughly 16 meters in total length, with a width of approximately 3 meters. Its extremely low ground pressure allows it to travel over deep snow, soft tundra, and even marshy terrain without sinking. One of its most remarkable features is its amphibious capability. The vehicle can swim across rivers, broken ice, and coastal waters, using its tracks for propulsion, a critical advantage in Arctic environments where ice conditions constantly change. The DT-30PM entered service in the late 1990s and early 2000s and has been used extensively by the Russian military, energy sector, and polar research organizations. It has supported missile system transport, oil and gas infrastructure construction, and scientific expeditions in regions inaccessible by any other ground vehicle. Its reliability and versatility have made it a cornerstone of modern Arctic logistics. Crew survivability was a major design focus. The forward unit typically houses the cab and crew compartment, equipped with advanced heating systems, insulation, and navigation equipment suitable for whiteout conditions. The rear unit can be configured for cargo, fuel tanks, mobile workshops, or living modules, allowing mission-specific customization. Historically, the DT-30PM Vityaz stands apart from earlier Arctic giants by achieving what many predecessors could not: operational success at extreme scale. It proved that articulated heavy vehicles could combine size, reliability, and adaptability, setting a global benchmark for Arctic transport and redefining what is possible in sustained polar ground operations. DT-30 Vityaz All-Terrain Carrier, a polar heavyweight with unmatched mobility. The DT-30 Vityaz All-Terrain Carrier is one of the most capable heavy Arctic vehicles ever developed, earning a reputation for combining immense size with extraordinary mobility in environments where terrain is unstable, frozen, or constantly changing. While closely related to the DT-30PM, the standard DT-30 variant became the foundational model that demonstrated the full potential of articulated tracked transport in polar regions. The Vityaz program originated from Soviet research into Arctic mobility during the 1960s to 1970s, when expanding industrial, military, and scientific activity in Siberia exposed the limitations of conventional tracked and wheeled vehicles. Engineers recognized that Arctic terrain demanded not just power, but flexibility. The solution was an articulated two-section vehicle capable of bending and twisting to maintain constant ground contact. The DT-30 consists of two tracked units joined by a central articulation joint that allows movement in both vertical and horizontal planes. This design enables the vehicle to climb steep ice ridges, descend into crevasses, and cross uneven snowfields without losing traction or stability. Fully loaded, the DT-30 can exceed 55 metric tons in total weight, with a payload capacity approaching 30 metric tons, placing it among the heaviest operational Arctic vehicles in the world. Measuring approximately 16 meters in length and over 3 meters in width, the DT-30 distributes its mass across wide tracks, resulting in extremely low ground pressure. This allows it to traverse soft tundra, deep snow, and partially thawed ground without sinking, a critical advantage in polar regions affected by seasonal temperature fluctuations. The vehicle is also fully amphibious, capable of swimming across rivers, flooded ice, and coastal waters using track propulsion, eliminating the need for bridges or ferries. The DT-30 entered widespread service from the late 1980s to 1990s, and has since been employed by military units, oil and gas operators, and scientific organizations. It has transported radar systems, fuel tanks, drilling equipment, and prefabricated structures to some of the most remote locations in the Arctic. Its reliability under extreme cold conditions, often below -50 degrees Celsius, made it a preferred platform for long-duration missions. Crew protection and endurance were central to the DT-30's design. The forward module houses the driving cab and crew compartment, equipped with robust heating, insulation, and navigation systems designed for whiteout conditions. The rear module can be configured for cargo, fuel, workshops, or living quarters, allowing rapid adaptation to mission requirements. In the history of polar transport, The DT-30 Vityaz stands as proof that size does not have to come at the expense of mobility. It demonstrated that massive vehicles could remain agile, reliable, and versatile in the most unforgiving environments on Earth, setting a standard that few Arctic vehicles have matched. A ATT Arctic overland train configuration, military power scaled into a polar convoy. The ATT Arctic overland train configuration was a practical yet imposing attempt to adapt proven military hardware into a large-scale Arctic logistics system. Rather than designing an entirely new vehicle, Soviet planners expanded the role of the ATT heavy artillery tractor, transforming it into the lead unit of multi-vehicle convoys capable of hauling enormous loads across frozen terrain. The ATT was originally developed in the early 1950s, entering service during 1952 to 1953 as a heavy military tractor designed to tow artillery, missiles, and engineering equipment. Its exceptional pulling power and rugged tracked chassis made it an attractive candidate for Arctic use at a time when the Soviet Union was rapidly expanding operations in its northern territories. Engineers recognized that by linking multiple sleds or powered modules behind a single ATT, they could create an overland train capable of transporting supplies deep into regions without roads or railways. During the late 1950s to early 1960s, experimental Arctic configurations were tested in Siberia and other northern test ranges. In these setups, the ATT served as the primary power unit, towing several heavy cargo sleds or tracked trailers loaded with fuel, construction materials, and equipment. Some configurations included heated living modules, allowing crews to remain in the field for extended periods. When fully assembled, these convoys stretched across significant lengths, rivaling early Arctic land trains in scale. The ATT's tracked design allowed it to operate in deep snow and uneven ice where wheeled vehicles were ineffective. Its wide tracks reduced ground pressure, enabling it to pull heavy loads without sinking into soft tundra or snowpack. The vehicle proved particularly valuable during winter months when frozen ground increased load-bearing capacity and allowed for longer, more reliable traverses. Despite its strengths, the ATT Arctic overland train configuration had limitations. Towing multiple units significantly reduced speed and maneuverability, and turning long convoys in confined terrain was difficult. Mechanical strain on the lead tractor increased dramatically under full load, leading to higher maintenance demands. Fuel consumption was also substantial, limiting operational range unless extensive fuel caches were established along routes. Although the ATT-based land train was never standardized as a single formal system, it played a crucial transitional role in Arctic transport development. The experience gained from these convoys directly informed later designs, including purpose-built articulated vehicles and integrated land train concepts. Historically, the ATT Arctic overland train configuration represents a pragmatic step in polar logistics evolution. It demonstrated how military power could be scaled into convoy-based Arctic operations, bridging the gap between traditional tractors and the massive, specialized polar vehicles that followed. Let 400 Arctic Land Train, a mobile base stretched across the ice. The Let 400 Arctic Land Train was among the most ambitious Soviet attempts to create a true mobile base for Arctic operations, conceived at a time when engineers believed that sheer scale and modular design could overcome the logistical isolation of the far north. Rather than relying on aircraft or seasonal ice roads, the Let 400 was envisioned as a ground-based system capable of sustaining long-distance travel and prolonged habitation across frozen terrain. Development of the Let 400 concept took place during the late 1950s to mid-1960s within Soviet Arctic and military engineering programs. It emerged from the same strategic context that produced other Arctic land trains, as the Soviet Union sought to support oil exploration, mineral extraction, scientific research, and military infrastructure deep within Siberia's Arctic interior. The goal was to create a vehicle system that could function as a rolling supply depot, workshop, and living space all in one. The Let 400 was designed as a multi-unit land train composed of a powerful lead tractor, connected to several large articulated modules. Each module was mounted on tracks or specialized low-pressure running gear to reduce ground pressure on snow and ice. When fully assembled, the train extended across dozens of meters, making it one of the longest overland vehicles ever proposed for Arctic use. Its sheer length allowed it to carry enormous quantities of fuel, cargo, and equipment in a single journey. A defining feature of the Let 400 was its emphasis on crew endurance. Some modules were intended to house sleeping quarters, kitchens, medical areas, and command spaces, effectively turning the train into a mobile base camp. This design reduced dependence on fixed stations and allowed teams to operate continuously for weeks or even months in regions where resupply was extremely difficult or impossible. Field testing and evaluation took place during the early to mid-1960s in Arctic and subarctic environments. The train demonstrated that distributing weight across multiple articulated units made it possible to move heavy loads over terrain that would immobilize conventional trucks. However, the system also revealed significant drawbacks. Maneuverability was limited, especially in areas with pressure ridges, uneven ice, or confined routes. Mechanical complexity increased with each additional unit, making maintenance and repairs challenging in remote conditions. Fuel consumption was another major concern. Powering such a large convoy required substantial fuel reserves, reducing overall efficiency and limiting practical range unless fuel depots were pre-positioned along the route. As a result, the Let 400 did not progress beyond the experimental and conceptual stage. In historical perspective, the Let 400 Arctic land train stands as a symbol of an era defined by bold engineering ambition. While it never entered widespread service, it contributed valuable insights into modular transport, crew habitation, and large-scale Arctic logistics. Its legacy lives on in later articulated vehicles and expedition systems that pursued the same goal with greater efficiency and practicality. MAZ 7310 Arctic Heavy Transport Vehicle, 8 axles built for polar megaloads. The MAZ 7310 Arctic Heavy Transport Vehicle was one of the largest wheeled vehicles ever adapted for sustained operation in extreme cold environments. Developed by the Soviet Union during the height of the Cold War, it embodied a philosophy that favored raw size, payload capacity, and mechanical robustness to meet the logistical demands of remote Arctic regions. While originally conceived for military and strategic purposes, its sheer scale made it equally suited for polar transport and expedition support. Development of the MAZ 7310 took place at the Minsk automobile plant during the late 1970s to early 1980s. The vehicle entered service in the early 1980s and was based on earlier MAZ heavy transporter designs, refined to carry unprecedented loads across undeveloped terrain. With its distinctive 8-axle, 16-wheel configuration, the MAZ 7310 measured over 22 meters in length and weighed more than 40 metric tons when empty, placing it among the largest wheeled land vehicles of its era. The primary strength of the MAZ 7310 lay in its payload capacity. Designed to transport loads exceeding 60 metric tons, it was capable of hauling oversized equipment, fuel systems, prefabricated structures, and strategic hardware across long distances. For Arctic operations, the vehicle was modified with cold weather insulation, reinforced drivetrains, and heating systems to ensure reliable performance at temperatures approaching minus 50 degrees Celsius. Despite its size, the MAZ 7310 was engineered to distribute weight effectively. The multiple axles reduced ground pressure, allowing it to operate on frozen ground, compacted snow, and ice roads without catastrophic sinking. This made it particularly valuable in winter Arctic conditions, when frozen terrain could temporarily support vehicles far heavier than conventional trucks. The MAZ 7310 was used extensively by the Soviet military, and later by civilian industries involved in oil, gas, and infrastructure development in northern regions. It played a key role in transporting massive components to remote sites where railways and paved roads were unavailable. However, its operation was largely seasonal, as thawing ground during warmer months severely limited its mobility. Operational challenges accompanied its advantages. Maneuverability was limited due to its length and turning radius, and fuel consumption was extremely high. Maintenance in remote Arctic environments required specialized support and trained crews, reducing flexibility compared to tracked vehicles. In historical context, the MAZ-7310 represents the upper limit of wheeled Arctic transport. It demonstrated that with sufficient scale and engineering, wheeled vehicles could compete with tracked machines in polar logistics. Though later designs favored articulated or tracked solutions, the MAZ-7310 remains a powerful example of 8-axle engineering built to move polar megaloads across the frozen frontiers of the world. MAZ-7907 Arctic Heavy Platform. Nuclear era mass-adapted for extreme cold. The MAZ-7907 Arctic Heavy Platform was one of the most extreme wheeled vehicles ever built, a product of Cold War engineering that pushed the limits of size, weight, and mechanical complexity. Conceived during the Soviet Union's nuclear era, it was designed to transport the heaviest strategic payloads imaginable across vast, undeveloped territories, including regions with severe Arctic and subarctic conditions. Development of the MAZ-7907 took place at the Minsk automobile plant during 1983 to 1985. The vehicle was created as a transport platform for ultra-heavy strategic systems at a time when mobility and survivability were central to Soviet military doctrine. Unlike conventional trucks, the MAZ-7907 was not merely scaled up. It was fundamentally reimagined to handle unprecedented mass while remaining mobile on imperfect terrain. The platform featured a remarkable 12-axle configuration, with 24 wheels driven by an advanced electric transmission system. Power was supplied by a gas turbine engine that generated electricity for individual wheel motors, a solution chosen to manage torque distribution across such an enormous vehicle. Fully loaded, the MAZ-7907 weighed well over 200 metric tons, making it one of the heaviest wheeled land vehicles ever constructed. In terms of dimensions, the vehicle stretched to nearly 30 meters in length and spanned more than 4 meters in width. Its size alone placed it beyond the capacity of most existing roads and bridges, which is why it was intended to operate in remote regions, including frozen landscapes where ice roads and compacted snow could temporarily support extreme loads. For cold weather operation, the MAZ-7907 incorporated extensive insulation, heating systems, and cold-resistant components to ensure functionality in sub-zero temperatures. Testing and limited operational trials occurred during the mid to late 1980s. While the platform demonstrated that such immense mass could be moved under controlled conditions, it also revealed serious limitations. Maneuverability was poor, fuel consumption was extraordinarily high, and maintenance demands were immense. The vehicle required specialized crews and infrastructure, making it impractical for routine deployment. By the late 1980s to early 1990s, changes in strategic priorities and economic pressures led to the cancellation of the program. The MAZ-7907 never entered full operational service, but its existence marked the outer boundary of wheeled vehicle engineering. Historically, the MAZ-7907 stands as a symbol of nuclear-era ambition applied to ground transport. Although not a traditional expedition vehicle, its adaptation for extreme cold and remote operation earns it a place among the largest Arctic-capable platforms ever built. It demonstrated both the possibilities and the limits of scaling wheeled vehicles to extremes, influencing later approaches that favored more practical articulated and tracked solutions for polar environments. Foremost, Terra Bus Arctic configuration, the largest low-pressure polar personnel carrier. The foremost Terra Bus Arctic configuration represents a fundamentally different approach to Arctic mobility, prioritizing surface preservation and personnel transport over raw traction or military power. Developed in Canada, it became the largest low-pressure wheeled vehicle, specifically designed to move people safely across snow, ice, and fragile polar terrain, without causing structural damage to the surface below. The Terra Bus was developed by Foremost Industries during the 1970s to 1980s, a period when Arctic tourism, scientific research, and environmental awareness were expanding rapidly. Unlike Soviet polar vehicles designed for hauling heavy cargo, the Terra Bus was created to carry large numbers of passengers into extreme environments while minimizing ecological impact. Its Arctic configuration was adapted for operations in polar regions where traditional tracked or high-pressure wheeled vehicles would damage ice fields or tundra. The vehicle's defining feature is its enormous low-pressure tires, which distribute weight across a broad surface area. This design allows the Terra Bus to operate on soft snow, ice sheets, and frozen wetlands with ground pressure comparable to that of a human footstep. In Arctic conditions, this capability is critical for maintaining safety and preserving sensitive environments. The Terra Bus measures over 14 meters in length and can weigh more than 25 metric tons when fully loaded, making it the largest low-pressure personnel carrier ever used in polar regions. The interior of the Terra Bus is configured to transport dozens of passengers in a fully enclosed, climate-controlled cabin. Large panoramic windows provide visibility in white, featureless landscapes, while robust heating systems ensure comfort in sub-zero temperatures. The vehicle is typically crewed by a small operator team and designed to function as a mobile observation and transport platform rather than a long-duration living vehicle. The Terra Bus entered service in Arctic and subarctic regions from the 1980s onward, and became particularly well known through its use in polar tourism and research logistics. It has been widely employed in environments such as the Canadian Arctic and Antarctic periphery, where minimizing environmental disturbance is a primary concern. Its reliability and gentle footprint made it a preferred alternative to tracked vehicles in regulated zones. Operational limitations are inherent in its design. The Terra Bus is not intended for steep terrain, deep crevasses, or heavily broken ice. Its size and turning radius limit maneuverability, and it is dependent on relatively stable snow and ice surfaces. However, within its intended operating envelope, it has proven exceptionally effective. In historical context, the foremost Terra Bus Arctic configuration stands apart from other polar giants. Rather than conquering the Arctic through brute force, it demonstrated that scale and environmental sensitivity could coexist. Its success redefined how large numbers of people could safely access polar regions, making it a unique and enduring contributor to Arctic expedition vehicle history. Caterpillar D-10 Arctic Expedition Tractor, bulldozer scale at the edge of the world. The Caterpillar D-10 Arctic Expedition Tractor represents the upper extreme of industrial earth-moving power adapted for polar environments. Originally designed as one of the largest bulldozers ever built, the D-10 became a critical tool in Arctic and subarctic regions where infrastructure, exploration, and survival depended on machines capable of reshaping frozen landscapes under brutal conditions. The Caterpillar D-10 was introduced in 1977. Developed by Caterpillar Incorporated to meet growing demands in mining, construction, and large-scale earthmoving. Almost immediately, its immense size and durability attracted attention from operators working in northern Canada, Alaska, and polar-adjacent regions. Arctic adaptations followed during the late 1970s to 1980s, as industrial activity expanded into colder and more remote territories. Weighing over 90 metric tons depending on configuration and attachments, the D-10 is among the heaviest tracked vehicles ever adapted for Arctic use. It measures roughly 7.7 meters in length and over 4 meters in width with blade installed. Its massive tracks distribute weight across a wide surface area, allowing it to operate on compacted snow, ice roads, and frozen ground without immediately breaking through the surface. This capability made it invaluable for preparing routes, leveling station sites, and maintaining winter infrastructure. For Arctic deployment, the D-10 received extensive cold weather modifications. These included reinforced engine heating systems, insulated operator cabs, cold-resistant hydraulic fluids, and specialized starting systems to ensure reliable operation at temperatures below -40°C. Visibility enhancements and enclosed cabins improved operator safety during whiteout conditions and extended periods of darkness. The Caterpillar D-10 played a key role in Arctic oil and gas development from the late 1970s through the 1990s. It was used to construct ice roads, prepare drilling pads, and support heavy transport convoys by stabilizing terrain ahead of wheeled and tracked vehicles. In expedition contexts, the D-10 functioned less as a long-distance transporter and more as a force multiplier, enabling other large vehicles to move and operate safely. Despite its power, the D-10 was not without limitations. Fuel consumption was extremely high, requiring extensive logistical planning. Mobility was restricted compared to articulated Arctic vehicles, and operation was generally seasonal, limited to periods when ground conditions were sufficiently frozen. Nevertheless, no other bulldozer of its era could match its ability to operate at such scale in extreme cold. Historically, the Caterpillar D-10 Arctic expedition tractor represents industrial dominance pushed to the environmental limits of the planet. While not designed as a traditional expedition vehicle, its role in enabling Arctic exploration, construction, and logistics places it firmly among the largest and most influential machines ever to operate at the edge of the world. Caterpillar D-9 Polar Expedition Tractor. Heavy infrastructure power in frozen terrain. The Caterpillar D-9 Polar Expedition tractor has long been one of the most influential heavy machines adapted for operation in Arctic and polar-adjacent environments. While smaller than the D-10, the D-9 earned a reputation for unmatched reliability, versatility, and survivability in extreme cold, making it a cornerstone of polar infrastructure development and expedition support throughout the 20th century. The Caterpillar D-9 was first introduced in 1954 and quickly became a global standard for heavy earth-moving. Arctic adaptations followed during the late 1950s to 1960s as industrial activity expanded into Alaska, northern Canada, Greenland, and other high-latitude regions. Its balance of power and manageable size made it particularly suitable for frozen terrain, where mobility, durability, and ease of maintenance were as important as raw force. Depending on configuration, the D-9 weighs between 45 to 50 metric tons and measures approximately 6.7 meters in length with a blade installed. Its wide steel tracks distribute weight effectively, allowing it to operate on compacted snow, ice roads, and frozen soil without excessive ground penetration. This made the D-9 ideal for preparing expedition routes, constructing runways on ice, and maintaining access paths for heavy transport vehicles in remote polar locations. For polar deployment, the D-9 received extensive cold weather modifications. These included engine block heaters, insulated and sealed operator cabs, cold-resistant hydraulic systems, and reinforced fuel and lubrication lines designed to function at temperatures below -40°C. Enhanced lighting and visibility systems were also critical, allowing operators to work safely during long periods of darkness and frequent whiteout conditions. The Caterpillar D-9 played a crucial role in Arctic exploration and infrastructure from the 1960s through the 1990s. It was widely used in oil and gas development, scientific station construction, and military logistics. In expedition contexts, the D-9 often operated ahead of convoys, leveling snowdrifts, stabilizing ice roads, and clearing obstacles that could immobilize larger transport vehicles. Its reliability made it a preferred choice in regions where mechanical failure could place lives at risk. While not designed for long-distance travel, the D-9's importance lay in its enabling role. Without machines capable of shaping and reinforcing frozen terrain, large Arctic vehicles and expeditions would have been severely limited. The D-9 provided the groundwork that allowed other giants to operate. In historical perspective, the Caterpillar D-9 Polar Expedition Tractor represents the practical backbone of Arctic operations. It lacked the spectacle of massive land trains or articulated carriers, but its consistent performance in the harshest conditions earned it a lasting place among the most important heavy machines ever used in frozen terrain.